Okay, today we will talk about the axial deformations on the members. But before going into that, remember that when we have a structure, let's draw a simple structure here. And this is an indeterminate structure. We have 6 unknowns here, and we said that we can write 3 equilibrium equations, meaning that I have to come up with 3 additional equations. And these 3 additional equations could be the compatibility equations. And the compatibility equations are equations that describes the deformation of a system, of a structure. And the other thing that we did is we said that we no longer look at this structure as a whole, but we divide it into members and nodes. So we have members and nodes. The reason of doing that is this member is a continuous member, and since it's a continuous member, I can describe its behavior, either the force behavior or the deformation behavior, by using some equations. And since we divide everything into members, I have to come up with equations that describes the deformation of a member. And we said that I have to come up with an equilibrium equation plus some equations to describe the deformation of a member. But the question is, how can I combine? I have equilibrium equations, equations that describes the compatibility. What is the relationship? How can I combine the forces with the deformations? And if we again go back to our strength of materials, we said that every action has a reaction, right? And the reaction that a member shows are deformations. And we classify the actions as applied loadings, we can have temperature change, etc. So these are all the external effects, and the response to these external effects are deformations. But we also classify the deformations, right? Because the deformation of a member as a whole is very complicated, so we classify it, we simplify it, and the way we describe the deformations are as follows. We said that we can have axial deformation, we can have flexural or bending deformation, we can have shear deformation, and we can have torsional deformation. So the way we describe the behavior of a member is as follows. A member could be subjected to some external loadings. Due to that external loadings, we will see some internal forces, and we said that these internal forces are abstract quantities. They really doesn't exist. You cannot measure them, you cannot see them, you cannot observe them, but what we observe is the deformations. And the way we describe the internal forces are, if we have axial forces that create axial deformations, we have moments that create bending deformations, we can have shear creates shear deformation, and we can have torsion on the member that creates torsional deformation. Now we will investigate these deformations, and I want to start with the axial deformation. So let's take a look at it. Now our aim here is, let's write the axial deformation. Our aim is to come up with a relationship at member level, okay? A relationship between the axial force and the corresponding axial deformation. So let's draw a member. Let's say that this is my member, and I apply an axial force to it, P, okay? And according to the description of our axial deformation, we said that axial deformation causes elongation or shortening in the member. So let's show the elongation. So due to that axial load, this member will elongate, and the amount of elongation is equal to delta. Now the question here is, what is the relationship between the applied load and the corresponding deformation, which is the amount of elongation in that case? Okay, and the way we do this relationship, we drive this relationship, has certain steps, and we will use these steps for every derivation. The first step is force stress relationship. So we will try to relate the forces with the stresses, and here it's very straightforward. Stress is equal to the applied force divided by the area. Okay. The second relationship, deformation strain relationship. We also call this kinematic relationship. So in order to do that, I will take an infinitesimal element, a small. This is the smallest piece that we can divide this structure into. And the length of this infinitesimal element is dx. Okay, so let's draw that infinitesimal element. This is the length of that element is dx. And we said that due to the applied loading, this will elongate. And the amount of elongation is d delta. So the axial strain is the deformation divided by the length of the member, that's d delta over dx. This is for the smallest piece. It is deformation divided by the length, and we are write it for this infinitesimal, the smallest possible piece of this member. And finally, I need a relationship between the stress and the strain. Sorry. Stress strain relationship. And we will assume linear elastic material behavior, and we have Hooke's law for it. According to that, I can write stress is equal to elastic modulus times the strain, the axial strain. Let's write it, axial stress, this is the axial strain. That's the relationship. Okay, so actually if you think about it, we have all the information that we need. So let's call this equation star. Let's call this one equation 1, and this one equation 2. Okay, so I will inserting equations 1 and 2 into equation star. So instead of stress, I'm writing P divided by A is equal to elastic modulus multiplied by d delta divided by dx. Okay, rearranging the terms, I have P times dx is equal to E times A times d delta. Okay, now assuming constant axial force and constant area through the length of the member. If we have the area is the same, the axial force is constant. Okay, with these assumptions, what I'm going to do is this. Now remember that this equation is written for this small piece. Okay, if I want to write it for the whole member, I will just have to add these small effects one by one, which means actually the integration. So I'm integrating them through the length of the member. So wrong equation, sorry for that. Let me erase this one. No. Let's work on the, yeah, I'm integrating this equation. Okay, when we integrate that, we have P is constant through the length. So this equation is P times L. I got P times L is equal to, now here in that equation, d delta, area is constant, E is constant. So integrate d delta over the length will give me the total deformation, and that's equal to EA times delta. If I rearrange this term, P is equal to EA divided by the length of the member multiplied by delta. And this is the relationship that I'm looking for. So this equation relates the axial force on the member with the axial deformation. So that's the equation that describes the axial deformation of a single member. In other words, if I know the axial force on a member, then from this equation I can determine the axial deformation. Okay, the second type of deformation that we are going to discuss is the bending deformation. In other words, the deformation caused by moment at a member. And the theory that we will discuss is called the Bernoulli-Euler beam theory. And in this theory, the shear deformations are ignored. Remember that you cannot have a moment without a shear force in a member. Okay, unless you have only a pure bending case. So if we have shear, we said that we will have shear deformations. If we have moment, we have bending deformation. But in the Bernoulli-Euler beam theory, the shear deformations are ignored. So this is a simplification. Okay. Now the way we will derive this relationship. Now remember that I'm trying to derive a relationship between the force, which is the moment, and the corresponding deformation, which we said it's curvature, and we will see why it is curvature here. Again, the starting point is in this derivation is force-stress relationship. Now I'm going to draw a section. Let's say that we have a rectangular section here. And that's the neutral axis. And I'll just put my coordinate axis to the centroid. That's X. That's Y. And this one is Z. And that's the neutral axis of the section. I'll say equal to, and I will draw another figure here, where I'll show the applied loading. X, Z, and Y. Okay, so here let's apply a moment. Apply a moment in the plus Z direction and try to figure out what will happen in terms of stresses at this member. Now this is the action. Now we are trying to figure out the abstract reactions, which are the stresses. So I will take an infinitesimal area, a small area here, okay, and whose area is dA, and at that area now this moment will create a compression at the top of the neutral axis, so I see compressive stresses in that area, okay, and the distance of this area to the neutral axis, this distance is y. If I take another infinitesimal area somewhere here, again that's dA, this is the smallest possible area in that member, and this moment, since we are below the neutral axis, will create a stress, a tensile stress here, and the distance of this area to the neutral axis will be equal to y again. Now for equilibrium, the moment created by all these little small stresses on this area must be equal to the applied moment. So let's write it as an equation. So moments about z-axis. So on the left hand side, the moment due to the single area or due to that stress. Let's write the moment due to that stress first. Force is sigma x. Now this is compression, so I should put a minus here. Times dA is the force applied to that infinitesimal area, and I have to multiply it with the moment arm, which is equal to y. So this equation is the moment due to that smallest piece. If I want to write the same thing for this area, in that case the stress will be positive, but the moment arm will be negative, so I'll get the same expression. Okay, now this is the moment of its infinitesimal area. So for the whole section, if I want to calculate it for the whole section, I have to add the moments of these infinite small areas, so which means that I have to integrate it, this one, through the whole area. And the equilibrium equation tells me that that should be equal to the moment. So as you see, this is my force stress relationship. On one side I have the corresponding force moment, and on the other side I have the axial stresses due to that moment. And I will call this equation as my equation star. Now we have the relationship. Let's write the stress-strain relationship. Again, I will assume linear elastic material. And I will be using the Hooke's law for this. And the stress, axial stress, is equal to elastic modulus times the axial strain. Okay, so let's call it equation 1. Now I have the force stress relationship, stress strain relationship. Now I need to relate the deformations, the corresponding bending deformation, with the moment, with the strains. Okay, so we call it as the kinematic relationship. if you take a piece of paper and try to bend it from both sides, you will see a curve, right? And the simplest way of describing that curve is a circular arc. And actually this is what we are using. We are using such an approximation to describe the bending deformation because it's the simplest way of defining bending. And because we only need a single parameter, okay, in order to describe the curve, how much curve you have at a certain length, all we need is a radius. If I know the radius and the center, I can define a circular arc, and this is what we do. So let's say that that's point O, and due to the bending, I see a circular arc. Okay, so this is the center line of the beam, right? And since we are assuming shear deformations, remember that the deformations do not cause any angle change. So if the section is initially perpendicular to the center axis, in the deformed state it will remain perpendicular. So these are still remain perpendicular. So I have another circular arc here and another circular arc here, and there is no angle change. And this is the centroid, center axis, or basically the neutral axis, and this distance is what we call the radius of curvature, and we show it by rho. Okay, and we are writing this deformed shape for a member that is under constant moment. Okay, let's repeat. We have a member that is under constant moment, and the way we define its deformation is as follows. We take the center line, which is the neutral axis of that member, okay, and we say that when I bend it by applying the same moments from both sides, and when I look at the deformed shape, I see a circular arc. All right, I mean, you may define this deformed shape in different ways. You can say that I see a parabola, right? A cubic parabola, quadratic parabola. I mean, that's also work. But the way we do in this theory is we see a circular arc. So we define this deformed shape with a circular arc whose radius is equal to rho. All right? Now, once we say that, let's say that that's point A. Okay, that's point A also. So I take a point somewhere in here. Let's call it B. Now, I see that point B in here. And let's say that at the same location, same height, I have a point C. So when I draw a line, I see another circular arc between point B and C, and let's say that this distance is equal to y. Okay, that's the center line. Let's label it. Let's call this point as A1 and that point as A2. So in the deformed shape, this is what we have, A1 and A2. Now, the length of undeformed bar. Is equal to, let's show it this way, A1, A2. Okay? And we are saying that, remember one of our assumptions, this is the small deformation assumption, the length of the center line, the neutral axis, doesn't change as it bends. Okay, so this length, A1, A2, is equal to that length. There is no change in length. Bending deformation doesn't cause the change in length for the center line. That's our assumption. So the name of that assumption is small deformation assumption. And I can write this distance is L, let's say. So L is equal to radius of curvature multiplied with this angle theta. So let me show that angle also. So the length of the member is equal to radius of curvature multiplied with theta. Okay. Now let's take a look at what will happen to this arc. We said that since this is at the neutral axis, its length doesn't change because we have zero stress at the neutral axis by definition. And if I go y distance away from that neutral axis, now this one is under compression, meaning that it will shrink. Okay, so let's write the length of that member, this fiber CB. So length of arc CB located at a distance y above the neutral axis so let's say that that's equal to CB, and let's call it L prime, and in that case L prime will be equal to, now we have a shorter radius which is equal to rho minus y, and I have to multiply it with theta again. Rho minus y multiplied with theta. Okay, so when I go from the fiber A1, A2 to CB, how much shortening will I see? So let's calculate it. So the deformation delta is actually the difference between these two lengths, right? Initially the fiber CB has a length equal to L, but as it deforms, it has a now L prime, so the amount of shortening in that member is equal to L prime minus L. And if you just put these equations into their places, we obtain the amount of shortening as y times theta. Okay. So let me write this one here one more time. So deformation at fiber CD is equal to minus y times theta. What about the strain? What about the axial strain? If I use the engineering strain definition, it is deformation divided by the original length. So deformation is minus y times theta, and the original length is radius of curvature times theta. These two cancel, and we end up with the following relationship: minus y divided by radius of curvature. And let's call this one the second equation. Now this relationship is very important, right? We have the strain and we have its distribution, and remember, while driving this, we didn't take a look at the material properties. We didn't look at the stresses. This is just geometry definition. And what does it tell us? If I draw the figure, this is the neutral axis. If I plot the variation of strain with respect to neutral axis, I'll get the following variation. It is minus y, rho, a linear variation. I have compressive strains here and tensile strains. Okay? Now, what is this angle? This is epsilon x, and this variation is y. In that case, what will be that angle? It is if I just put y here, I'll obtain that angle as 1 over rho. Will be the angle of that shape, and we call that angle as our curvature. If you bend more your member, your curvature increases and you get a more deformation in your member. Okay, so that's what we call the curvature, and that's the way we show it in the strain diagram. Okay, now as you see, I obtain a relationship between my deformation, which is rho, and the strain. Now I'm ready to combine it with these two equations. Okay, now inserting equation 1 into star, I have this moment is equal to integrate through the area y times elastic modulus times the axial strain, this is minus, times dA. Let's call it plus. Now as a second step, inserting 2 into plus, then I have the following relationship: A y times minus elastic modulus. So instead of strain, I'll have minus y rho dA. And if I write it in a more compact form, I can say that moment is equal to elastic modulus is constant, radius of curvature is constant, and I have the following integral: y square dA. Okay, now the next question, what is this equal to? That's a sectional property, the second moment of the area, or we call it as moment of inertia. We calculate it as a sectional property and we show it with I. Then I will just rewrite that equation. I'll have the following relationship: m divided by EI is equal to 1 over rho, or the moment divided by elastic modulus, material property times sectional property, is equal to this angle or the curvature. But I still do not like this equation, because what is curvature, radius of curvature equal to? I have to relate it with some, with the coordinate axis, with the deformations, right? The deformations that I have could be the vertical translation. I need that relationship. So for that we go to the calculus. Let's say that I have a curve and I divide this curve into small, very small pieces. Okay, this is usually the approach we take. And when I divide it into smaller pieces, what I see is very small circular arcs, and these circular arcs can be defined by the radius. If it is very close to the straight line, then I have a larger radius, or it's very curved, then I should have a very small radius. Okay, so these are all radiuses. And if I want to represent, write the equation of this curve in a Cartesian coordinate system, the relationship between the variation of these radiuses and the equation of that curve is as follows. Curvature, or which is equal to 1 over rho, is equal to dy square divided by dx square divided by 1 plus dy over dx to the squared and to the power 3 over 2. Let's go over one more time. I have a curve, an equation like this, which gives me a curve, right? This is the y of x. And when I divide this curve into very small pieces like that, or anywhere, very little tiny pieces, I see a small circular arc, and I define these circular arcs with these radiuses. Now the relationship between the variation of this radius and the equation of that curve is as follows. Okay, and again, this 1 over rho equal to that 1 over, it's the same thing. Now, but we can actually simplify that equation, because we are assuming that this is the deformations in our case is very small. If the deformation is very small, in other words, the transverse deformations are very small, this is a small number, and when you take the square of that small number, it will be a much smaller number. So for, if I can just say this, for small deformations I can ignore that. And I obtain a much simpler equation. Then the curvature is equal to, again, 1 over rho, and that's equal to d square y divided by dx square. For small deformation, that's the relationship between all these little radiuses and the equation of that curve. So if we consider the equation of that curve as the transverse deformation equation, from it, if we take the second derivative of it, we get the curvature, which is actually that angle. Now all I need to do is to put this equation into this one, and as a final case I obtain the relationship d square y divided by dx square is equal to m over ei, and that's also equal to curvature. And this is the relationship that I am looking for. This is the internal force that creates bending deformation, which is moment. Okay, and that's the corresponding deformation, which is the curvature. This is not minus, this is equal to. Okay, so we are saying that according to this theory, the deformation due to the moment is curvature. Remember, in the axial deformation case, the deformation due to the axial force is the amount of elongation. In the bending case, the deformation due to the moment is curvature, which is that angle. And that's the governing equation. In the axial deformation, we get a very straight relationship, but when it comes to the bending deformation, we have a second order differential equation. Okay, let's start discussing the third type of deformation, which is the shear deformation. Remember that in the Bernoulli-Euler beam theory, we ignore the shear deformation, but when we start considering the shear deformation in the beam theory, this is called Timoshenko beam theory. And we will see how we will consider these deformation, and then we will see how we can derive the stiffness coefficients. And let's put a note here. Of course, in the Timoshenko beam theory, we consider the shears. I'm not going to write that. We'll start the same way. We will try to figure out the force-stress relationship. And we said that the shear forces will create shear deformations. Okay, so let's draw a figure. Again, I'll use a cantilever. And I will apply a tip load in the upward direction. Let's say that that's B, that's point A, and that's point B. Okay, so let's draw the section of that beam. And here we have the neutral axis. So what I'm going to do is I'll take a section cut somewhere here. That's point C. And then draw the free body diagram. Let's say that's our second figure. I'm not drawing the whole free body diagram. Let's say that this is the neutral axis of that beam. I'm taking a piece at the top of the neutral axis and it continues towards point C. So I'm drawing the free body diagram of this part in figure 2. Okay, so I'll just use a larger scale now. So that's that piece. And here we have the neutral axis of the beam. And let's show the forces on this small piece. Okay, and this length is X. Now here we have some portion of that force, let's call it P prime. So in order to balance it, I should have a shear, let's call it V prime. And we know that this P will create a moment, and due to that moment, we will see some axial stresses here. So we are at the top, we should see some axial stresses as follows. Let's sigma X d A. And I should have, since I cut it here, I have these forces, right, due to the moment. In order to balance these forces, I should have an horizontal force, H. Now, let's write the force equilibrium, but before going into that, let's show what dA is. So I'm just looking at this slice. This slice is dA, and its distance from the neutral axis is y. Okay. Now let's write our stress relationship. Stress is equal to minus, this is compressive stress, that's why it's minus my divided by I. And in that problem, we know that moment is equal to axial force times x. So I'm just inserting that and writing the equation for this little piece. So sigma x times dA is equal to minus, instead of moment, I'm just writing P times x times y divided by moment of inertia times dA. So I have this following equality. Now, using the free body diagram of figure 2, I can write sum of forces in x direction must be equal to 0, right? So this gives me that the H horizontal force minus, I'm integrating the this sigma x times dA should give me the total force, and instead of sigma times dA I will write this expression, and that's equal to P times x y divided by moment of inertia times dA, that's equal to 0. So this minus is this minus, right? We have the directions all included. So from that equation I can write the following: that horizontal shear force is equal to P is constant x divided by moment of inertia integrated with y times dA. Okay, so what is y? So for this free body diagram, this is, let's call this distance as y1, and this is the section under compression, so this is total C. So I'm doing that integration from y1 to C, right? So it's, we are saying that I'm integrating that stress portion is from y1 to C. So if you take a look at this expression, what is this? So we call this as a with Q, and it's the first moment with respect to neutral axis of the cross section about the neutral axis. Okay, so I will continue from the right hand side. I can rewrite the following equation as follows: H, the horizontal force, horizontal shear force, is equal to P times Q is the first moment divided by the moment of inertia multiplied by x. Now, this is called, we name it as Q, and it's shear flow. And what shear flow represents is the following. Let's write its definition by looking at this equation. For a given value of y, the horizontal shear per unit length, so we are talking about this h over x, is constant, right? And denoted by Q. So let me write what Q is one more time. Q is equal to P times Q divided by I. Of course, we write this equation for this, for this very specific loading, but imagine you have a beam under different types of loading, and I can rewrite this equation in the following form. So for a beam under a more general loading, let's call this equation star. We can write equation star as follows. Instead of P, we will have Q this time, sorry, V this times. Okay, and I'm going to call this equation 1. So this is the general equation for the shear flow. What is shear flow? It's the horizontal shear per unit length. Okay, it is that shear per unit length. That's what we call the shear force. Okay, now we obtain a relationship between shear force and the shear flow, but still I will need a relationship with the shear stress. So let's do that. Now I will draw the beam section, or the beam one more time. You can imagine this as the bottom part of the section cut, or this portion. Okay, now we see the top part. Now I'm drawing this bottom part. Okay, so what will happen, and I will take, let me finish the figure. So I will take a slice. Okay, and this distance is delta x. And the way we will see the shear force distribution, the horizontal shear distribution, is as follows. That's what we see. Okay, when you write everything in 3 dimensions, and I should have this same shear distribution in this face. So what I did here is, remember, we always show the shear as follows, right? That's the shear force. So I drew this shear, this diagram in 3 dimensions. So this area delta area, right? But there's a variation in the shear, but I will just approximate it. Let's use an average shear, tau average, and I should have the same tau average for the top. Okay, and at the bottom, this is what I see, delta H for a unit length. Now, according to our the equations that we derived, H is equal to shear flow times X. So let's write it here in an incremental form. Delta H is equal to shear flow times delta X. And we know that shear flow is equal to V times Q divided by the moment of inertia multiplied by delta X. That's the horizontal shear force in terms of the vertical shear. And what is the average shear stress? It is the horizontal shear force divided by the area, and that's equal to delta H divided by delta area. So let's call this equation 2. Now inserting equation 2 into into star and rearranging the term, we get the following. I think I did the opposite, so let's correct this. Inserting equation double star into 2, I got stress as equal to V times Q times delta X divided by delta area is equal to delta X times B. So let's write it. Delta X times B, and I should have the moment of inertia at the bottom. So that's the equation. These delta x's will cancel each other, and then I'll obtain the following relationship. That's our stress force relationship. The average shear stress, of course, we are not looking at the variation. The average shear stress is equal to shear force multiplied by the first moment divided by the moment of inertia multiplied by the width of the section. And this is the applied force internal stress relationship. Okay, so we find out the force and stress relationship. Now the second step is the kinematics. I'm trying to relate the shear deformation with the shear strain. Okay, so for that I will take an infinitesimal element. So initially it was a square, and the length of the element is dx. Okay, and according to our definition of shear deformation causes only angle change. So we will just show it this way, because we are solving the member in one dimension through the length, and this is the shear deformation. That's what we call the shear strain, and this distance is called dvs, and its name is shear induced displacement. So relationship, the tangent of the shear strain is equal to dvs shear deformation divided by the length of the infinitesimal element. So assuming small deformation, so with this assumption I can write this: the tangent of the angle is equal to the angle itself. So I obtain my shear strain and shear deformation relationship. And we have to also determine the stress strain relationship. Again, we will be using the Hooke's law for elastic material. And the relationship between the shear stress and the shear strain is as follows. This time we will be using the shear modulus. Okay, now I have the stress force relationship, I have the shear strain corresponding deformation or the shear deformation relationship, and I have the stress strain relationship. So when I combine all these relationships, let's write combining all three relationships, we have the following. So shear strain is equal to shear stress divided by G. So dVs over dx is equal to V times Q divided by G I times E. So that's the final equation, but really I don't like this one. I don't like the form of this one. Why? Let's remember our previous relationships. We have P is equal to E times A divided by L times delta. This is for axial. Or if I write in terms of delta, I got PL divided by E times A. Now let's take a look at the bending deformation. D square y divided by dx square, that's our curvature, and it's equal to m divided by EI. So here what we see in common, this is a member property, that's a material property, and that's a sectional property. In the second case, this is a member property, this is a section property, sorry, material property, and we have a sectional property here. But this is a little bit complicated for me. I got material property, a sectional property, another sectional property. I have G here, and G is an integration with respect to the deformation. So this is a complicated equation for me. So what I'm going to do next is I will introduce some approximation, of course, but simplify that expression. That's my aim now. So my purpose here is, let's try to represent stress, that's a complicated term, VQ over IB in the form of shear stress is equal to force divided by some version of the area, where AS is called effective cross section. Okay, let's repeat. I don't like this form, it's too complicated. We have Q, and if you take a look at what Q is, it is this one, and I got I got B, and so on. So I'm trying to simplify it. In order to simplify this equation, I'm looking at this simplification, and I have QIB here, but instead of using QIB, I'm asking this, can I simplify it with a single parameter, with AS? And if you look at that equation, I have stress here, force divided by area. Now the question is, what is this area? How can I determine what this area is? So let's see. Now I'm taking a rectangular section. So for a rectangular section, I'm drawing it now. Right, I'm just drawing the similar figure as I did before. This is the neutral axis. This is the total height of the section. That's the width. This distance is y, and this is dA. So shear stress is equal to V times Q divided by moment of inertia times B, where Q is equal to integral from y to c is h over 2, y times dA, and for this case it's equal to b times y h over 2 y times dy, and then you evaluate that, Q is equal to b over 2 h square over 4 minus y square. Okay, so for a rectangular section like that, this is the Q, variation of Q. Now put it into that equation. I will have shear stress as equal to V over I times B multiplied by B over 2 h square over 4 minus y squared. These two b's will cancel each other. Okay, now when I plot the variation of shear stress, in other words, I'm plotting this equation, I obtain a shape like this. This is the depth. Now I have the neutral axis here. When y is equal to h over 2, it is 0. When y is equal to minus h over 2, it is 0. And in between, I have a quadratic variation. That's the variation of shear stress along the depth of the member. Okay? Now, instead of using it, can I do this? That's the question I'm asking. Or instead of writing the equations in this form, can I write it in the following way? shear stress is equal to V over some factor multiplied by A. Okay, so for this specific case, 1 over lambda is equal to area divided by 2I, h squared divided by 4 minus y square. Okay, now instead of going over all this, if I average this shear stress, now I have a constant shear stress, and the question is, what is the magnitude of that constant shear stress? So in other words, instead of using lambda as this one, I'm averaging it. Okay, I'm using a single value, and I'm asking this: if I use a single value, what would be the value of that lambda? Okay, and for different shapes, you repeat that procedure over and over, and we come up with the following representation. We say that tau is equal to V divided by the effective area for shear, and we define the effective area for shear as times the total area, and this lambda, of course, according to this, it has a variation, but when you do an averaging like this, equate the areas under these two shapes, we obtain lambda as equal to 5 over 6 for rectangular sections. So for different, if you have a different shape, you repeat that procedure, you calculate the Q, you determine the variation in the shear distribution, you equate the areas underneath and come up with this lambda value. But usually, if it's rectangle, we use lambda as equal to 5 over 6. Now, if we come back to this equation, one more time, now instead of using this, I can write the following. So instead of using that portion, we have G here. Okay, I can write the following equation. So as a result, simplified version is as follows: dvs divided by dx is equal to v divided by g times as, and this is the differential equation for shear deformation or shear versus deformation relationship.